Okay, this is lecture 25. We're going to talk about some steady state examples, so calculating steady state for a couple of different examples. Okay, so remember what we did, how we actually computed the steady state pi. So if we had an irreducible Markov chain, then we said that there was a unique stationary distribution pi such that p pi equals pi, and we called pi the steady state distribution. So here we did some examples last time where we talked about like the wildfire example, and we could calculate the steady state using powers. So for example, we calculated p to the 20th. We noticed that all the columns were the same, and these columns actually gave us the steady state. So let's do a similar example. Okay, so this is an example of a hopping frog. Okay, so you're assuming that you have a frog up here on vertex 1, and it's gonna hop. And so the question is where is it likely to be at after many, many hops? So you can think about if the frog starts here, then in just a couple hops, it's more than likely going to be just at one of the places close to it. So after a small number of hops, the frog will tend to be close to the starting position. So then what happens if I do a lot of hops? So here's this table here that actually does a lot of hops. And so here after one step, you have equal probability of being either at the 25 or at the 2 because you're going to go one way or the other. The frog's going to hop one way or the other. Now, when you have more steps, then you're still close to these ones that are right here around the frog where it started initially. But notice after about 400 steps, notice that they're all about the same. So that all of the different state spaces, I'm about equally likely to be on this lily pad as I am a lily pad over here or down here. Then I'm about equally likely as being at the top versus being here at the bottom, which is about as far away from my starting spot as I could get down here at this 14 and 13 and 14 here. So tends to be uniformly distributed on all the vertices. So we have this stationary distribution. So the starting position in this case really didn't matter, right? So if the frog started here, it doesn't matter in the long term where it started. It still had this unique stationary distribution because I could have started over here and I would have had the exact same stationary distribution after we started. Okay, so now another example. Let's suppose we're talking about motor vehicles. And so let's suppose we have 3 different motor vehicles that we're interested in: General Motors, Ford, and Chrysler. And each produce a new SUV. So we have these facts about who's going to move and who's going to stay with what they know. So General Motors keeps 85% of its customers, loses 10% to Ford and 5% to Chrysler. Ford keeps 80% of its customers, loses 10% to General Motors and 10% to Chrysler. Chrysler is not as successful. They only keep 60% of their customers, and they end up losing 25% to General Motors and 15% to Ford. Apparently, their SUV was not as good, and the customers decided to leave them. So anyway, they wanted to find the distribution of the market in the long run, or the steady state vector. Okay, so the first thing we have to do here is, all we have is a bunch of information, right? So as always, we have to start off with our typical, let's draw a transition diagram. So if we draw a transition diagram, we have 3 different states: General Motors, Ford, and Chrysler. And so here, this just gives our transition. So here, General Motors, if you're with General Motors, you have 85% chance of staying with General Motors. You have 10% chance of going to Ford, and you have a 5% chance of going to Chrysler. And so similarly, you get something for Ford and something for Chrysler here. So once we have this, we can actually also write down the probability transition matrix. So we have this transition matrix where here, if I'm here at General Motors, the likelihood going to General Motors is 85%. Going to Ford is 10%, and going to Chrysler is 5%, etc., etc. Okay, so how do we find the steady state? Let's look at the steady state using powers. So here, if I take my P matrix, I plug it into MATLAB, and I do P squared, this is what I get. Notice that my columns do not look anywhere close to being alike each other. P cubed, still not p to the 20th, they're getting closer to each other, so you can start to kind of guess what maybe the steady state might be, but they still aren't identical. So you keep on going. And even here, they're obviously a lot closer with p to the 25, but they're still not identical. So if you just jump on up to p to the 100, then you get identical columns. Let's just make sure p to the 200 is still identical. It's the same values. So here our steady state is that General Motors has about 49%, Ford I think is 30%, and then Chrysler has 15%. So let's just, for the sake of it, calculate it a different way, and I'm going to show you how to actually use MATLAB to calculate the p pi equals pi. So here I can define my mat p by saying basically I'm taking the p minus the identity matrix. Remember, that's how I got things before, was I took the p minus my identity matrix on the last lecture. So I'm going to define that to be my mat p, and then I want to add in those ones, because remember I'm going to have that sum equal to 1. So here I add in the sum, so I'm thinking about pi 1, pi 2, and pi 3 all sum into 1 here. But I don't have my right hand side, so I have to get my right hand side. So I want my right hand side to be 0, 0, 1, right? Because I made the p minus I p, and that should be equal to 0, and then I have all of them should sum to 1. So here I had to add in that right side. I call this matrix augmented. Once I have my augmented matrix, then I can find my reduced or echelon form of it. And here's my steady state. And notice it's the exact same thing as what I had before. I get the same steady state and come to the same conclusions that in the long run, General Motors is likely to be out on top, more than likely because they were able to retain their customers. Okay, so this is kind of a different example, talking about umbrellas. So you have a professor who has 2 umbrellas, only 2 umbrellas to their name. And so she uses them only when it rains to commute from home and to her office. It rains with a probability p. So the question is in the long run, what's the probability that she's going to get wet on a given day? So basically, if she doesn't have an umbrella and it rains, she's going to get wet. Okay, so let's start off with what's the probability she's not going to have an umbrella. Okay, so she commutes between home and her office, so we're going to kind of look at this a different way. We're going to look at it in terms of the states of the umbrellas. So she's either going to have 0 umbrellas, 1 umbrella, or 2 umbrellas. We really hope she doesn't have 0 umbrellas when it rains. So, but these are different states, 0, 1, and 2. And then we're going to look at it as home and office. So these are the 2 places that she commutes from. She's either at home or she's at her office. So at home, she can have either 0, 1, or 2 umbrellas. Which means that if she has 0 umbrellas at home, then she would have 2 umbrellas at the office. If she had 1 umbrella at home, that means 1 umbrella is at the office. 2 at home, that means she has none at the office, right? So if you're in this case or this case, and you're trying to go from one or the other, then you're going to have a little bit of a problem. Okay, so now let's see how we transition from one to another. Well, let's start down here at the bottom. Let's assume she's home. Let's start at the bottom here, and then I'll show you how to get this into a traditional format. Okay, so suppose you're at home. You have 2 umbrellas. So if it rains, then you're going to take one of those umbrellas to work. So you did have 0 umbrellas, right? But you took one of your umbrellas from work home, so now there's 1 umbrella left at the office. The probability of rain is p. So if it doesn't rain, then you're going to stay just like you are, and so you're going to stick with 2 umbrellas at home and none at the office. Okay, so now if I'm at home with 1 umbrella and it rains, then I'm going to end up with 2 umbrellas at the office. But if it doesn't rain, then I'm going to keep it the same. And if I have no umbrellas at home, then it doesn't really matter, because if I'm going to the office, then if I have no umbrellas at home, then I'm going to keep with only 2 umbrellas at the office. So here, our traditional diagram, we really only have 3 states, right? We can't think about this as home and office. We really have 3 states. So what's the likelihood of transitioning from 0 to 2? Well, this is probability of 1. So if I have 0, I'm going to transition always to 2. And here, if I have 2, then if it rains, then I'm going to transition to 1. Otherwise, I'm going to transition to 0. And then here, if I have 1, if it rains, I'm going to transition to 2. Otherwise, I'm going to keep it at 1. So this is how you take this kind of setup and you do your transition diagram. So we have that. We can actually write down a probability matrix. And so here again, we're thinking about this as starting at 0, 1, 2. So we need to find pi. We can't really use powers because we haven't actually been given a p, so we can't really plug it into MATLAB. And you can use something like Maple and symbolically do this, but I just find it easier to do it by hand. Okay, so in order to find the steady state, we're going to do p pi equals pi here. So just looking at what we have, here is our p pi equals pi. We can simplify it. So what we have here is 1 minus p times our pi 2 has to be equal to pi 0. If I multiply the second one out, I'm going to have 1 minus p times pi 1 plus p times pi 2 has to equal pi 1. If I look at what this third one tells us, it tells us that 1 times pi 0 plus p times pi 1 is going to have to be equal to pi 2. And I always have that their sum has to be equal to 1, so that's always a given. Okay, so now that I have this, I've got to figure out how to simplify. So really what I'm going to do is I'm just going to look at it kind of individually. So if I take the second equation and I move things around a little bit, then notice what I get is just this simplifies down to pi 1 has to equal pi 2. So if I think about moving this over to the other side, I'm just left with p pi 1 is equal to p pi 2, or pi 1 has to equal pi 2. Okay, so now I use that in my top equation and my bottom, my first and my third equations. So I use it in my first, so I use it here and I use it in here and here, and notice they reduce down to be the exact same thing. So these two equations collapse down into 1 minus p pi 2 has to be equal to pi 0, because once I stick this pi 2 in here, I get pi 0 is equal to, I bring this p pi 2 over to the other side, I have 1 minus p pi 2. So it's the exact same equation. So then I can look at this last one here, again thinking about my pi 1 is equal to pi 2, and so what I end up with is pi 0 plus 2 pi 2 has to be equal to 1. Okay, now I have two equations and two unknowns. I can take them and I can solve for either pi 0 or pi 1. So what I did is I actually stick in my pi 0, I have my pi 0 here is equal to this, I stick it down here, I can solve for pi 2, I get pi 2 is 1 over 3 minus pi, so I can solve for all my rests now. Because once I have pi 2, I can find pi 1, once I have pi 1 and pi 2, I know what pi 0 is supposed to be, so I have this steady state. Okay, so now let's go back. The question was, in the long run, what was the probability that she gets wet on a given day? So, what have I calculated? Have I calculated the probability that she gets wet? No, but I can tell you in the long run what's the probability of having no umbrellas, having one umbrella, having two umbrellas, which is a start. Okay, so if I want to get the probability of getting wet, then that's the probability of having no umbrellas times the probability that it's going to rain. So you have to have two things happen. You have to have no umbrellas, and then you have to have rain. So the probability of getting wet, again, just what I just said, probability of having no umbrellas times the probability of having rain. So what we had for the steady state, we had these values for the steady state. Really, we're only interested in the probability of no umbrellas, which is this first one here. So this is the probability of having no umbrellas. And then we have the probability of rain is just p. So the probability of getting wet is just 1 minus p over 3 minus p, all times p. Okay, so our last example here is graduation. So you have this university administrators have developed a Markov model to simulate graduation rates at their school. So students drop out, repeat, move on to the next year. They have 3% chance of repeating the year. First year and sophomore is 6% chance of dropping out. And juniors and seniors drop out at a less rate of 4%. So once you're invested a little bit longer, they assume you're not as likely to drop out. Okay, so if we look here, you have 6 different states. So you have dropout, you have graduation, and then you have all of the in-between, freshman, sophomore, junior, and senior. You have all the transition rates that go along with this. So you're either going to repeat, you're going to drop out, or you're going to move, or you're going to stay, or you're going to move on. So you can write down the probability transition matrix for this. So here's our probability transition matrix. So if we look, the long-term probability, there's 2 absorbing states. So you're assuming once you drop out or you graduate, then you're not coming back. So really what we want to do is estimate the long-term probability that the student will graduate. So we're still looking at long-term probability, but not quite the same. We can note this isn't a recurrent Markov chain because it has 2 absorbing states. So it's no longer recurrent, and so we've got to kind of think about it a little bit differently. So here we're interested in, if you're in a certain state, what's the likelihood of dropping out? If you're a freshman or sophomore or junior or senior, what's the likelihood of eventually dropping out or eventually graduating? Okay, so let's look at the method of powers. Let's see how that works for us. So here's our P. This is the exact same thing we had before. We put in MATLAB. We do P to the 5th, so this is kind of giving us the probability of what happens in 5 years. So in 5 years, if you started out as a freshman, then you have about 19% chance of having dropped out and 80% chance of graduating in 5 years. Now notice if you started out as a senior here, so here, you started out as a senior, then you have about 96% chance of having graduated and only 4% chance of having dropped out. That's really good. So junior, you have a good chance of having graduated in 5 years. Sophomore, you might still be there. And then freshman, you may still be there. More chance of dropping out as a freshman than the other years. You have very little invested at that point. Okay, so if I look at P to the 10th, then what I can see is the rows of the matrix are not identical, which means the long-term probability of hitting a particular space really does depend upon your initial state. What I have is if I look, everything up here is 0. All I'm left with is my absorbing states. So these 2 rows represent my absorbing states, right? This one gives me my probability of dropping out, and this bottom one gives me my probability of graduating. So instead of staying in one of the classes, I'm going to go to the absorbing state, and I'm going to stay in the absorbing state. So this is my steady state. Next time we're going to actually talk about how long it actually takes to get to the absorption.